So, good afternoon, or it's afternoon for me. It's Sunday. Beautiful day outdoors today, and this is probably what it looks like down in Kingsburg, but I'm not there right now. This is from back during the break. That uh, This is Kingsburg Beach, looking across from area called Rose Head. Dora's down there right now. My wife's down there for 2 weeks. So let's get on with our show here. What is March the 6th? Well, no homework day. That'd be good. Uh, anyway, and it's National Oreo Cookie Day. And I don't know about you, but when I was a kid, Oreos were an incredibly special treat for us that we didn't get them very, very often. Few events taking place on campus this week. Tuesday, career conversations. I'm not sure what that covers, but you should be thinking about your future, even though you may be in your first year. Um, you got to figure out where you're going. And you can keep changing your mind as you go. But you should be developing some thoughts as to where you'd like to be. And there's a expression from Alice in Wonderland when Alice asks for directions from the Cheshire Cat, and she wanted to know which way should I go. And the cat asked, "Well, where do you want to go?" And she replied, "Well, I don't think it matters." And he told her, "Well, then it doesn't really matter." Anyway, it's also International Women's Day on Wednesday, and there's a lecture in Theater B if you'd like to attend. And I'm not sure what that is going to be covering and who's speaking. But anyway, on with the show. Assignment 3, it's going to be due on Friday. I've got a tutorial for Tuesday at 1. Most people just view the recording, as I've said before, and I'll keep repeating. You don't really learn anything unless you try the question before you look at the tutorial. Please try, you know, even if you got stuck and you watch the tutorial, you got unstuck again, then turn off the tutorial, get on, work through the assignment, then go back. And as you get stuck, go and bring it up. Um, and there's a discussion due on Wednesday. So, a few things. These were questions I had set up initially for today, but then we did write the test on Friday, and I've got a few more questions taken from that. So let's go through a few of these. So in simple linear regression using OLS, what does OLS mean? Are we trying to minimize the average absolute prediction error, penalize big errors by squaring them? We look for any relationship between two variables or all of the above. What does OLS stand for? Called ordinary least squares. That should be your cue. You're trying to minimize squared error. So it's not the average absolute prediction error. It's the average squared error. And so we are penalizing big errors by squaring them. We aren't looking for any particular relationship. Um, we're estimating a line between two variables uh, using a straight line, but it's not any relationship we're looking for. So what's not true? Now, these questions are always the most difficult when I ask you something that's not true. So 3 of them are true. Well, with multiple regression, it assumes a linear relationship with each variable. It can only be used with numeric variables. It assumes that the terms in the model are additive, and it's a popular method of value estimation. Definitely, it's a popular method of value estimation. And it does assume a linear relationship with each variable. And so that's, in a sense, why we'd say the different terms are added together. That's what linear models are like, is you don't multiply things, you just add them all up. Can only be used with numeric variables. Well, we can have categorical variables like gender, and then we just code it. It's 0 and 1. So we create a binary variable for those categorical ones. So B is not true. So when building regression models, Nominal variables such as gender and ethnicity, they can be added by assigning numbers to each label, cannot be included because they're not numeric, are easiest to include for binary variables, yes, no, or none of the above is true. Well, we just showed that B was not true because we can code them like 0, 1 for binary ones. And so C is true. A, yeah, we're assigning numbers 0, 1, but they're not just any numbers. So if we had ethnicity, where you've got Caucasian, Asian, African American, an example in class, I couldn't do 1, 2, 3 or 0, 1, 2. That won't work. I have to code them as binary things, yes, no. If a variable has a negative coefficient, then the R square is going to be lower than if you didn't have it. Predicted value will decrease as this variable increases. Something's wrong when a coefficient is negative, or none of the above. We can have negative or positive coefficients. Negative coefficients means a negative slope. It means that as x goes up, as we're making x bigger, y is going to go down. It's a decreasing function. B is true. So here were 3 from your tests that people had difficult time with. So you were given a model that's predicting, these were medical expenses, I think, that for a client based upon their age, and as you're given the basic output that's there. So I've got 3 statements here, and lots of people jumped for the wrong ones. The right one was C. So that the expenses of 97.7% of those that are age 50 will be approximately 9,898. Where did the 97.7 come from? Oh, that's your multiple R. Well, we're not using it. And it doesn't have anything to do with how many people it applies to. That and R square, the next one it says 95.4% of 50-year-old clients will be approximately 99, 98, 98. No, R square has nothing to do with how many observations are this, that, or something else. The average expenses for all 50-year-old clients will be approximately 98, 98. That's true. It represents where the line goes. And so there's some scattered above, some below. The average, that's where the line is. The line represents the average. And then this last one, the average of all of them, again, it's using an R squared term. R squared does not tell you anything about how many. So here's another one from that test. So you have 2 clients, one age 40, one age 50. So the model prediction will be 8291 less accurate for the 50-year-old client compared to the 40-year-old. Where does that come from? Not quite sure. 8291. Maybe that was a prediction of something. I don't know. The predicted expenses for the 50-year-old will be 19.01 higher than the 40-year-old. Lots of people pick that one. Where'd they get the 19.01? Took the standard error and multiplied by 10. No, standard error represents accuracy of something. It's not to do with the 2 groups. The predicted expenses for the 50-year-old will be $2,691 higher than the 40-year-old client. Yeah. The coefficient for age is 269. So for each additional year, expenses rise by $269. So the 40-year-old and the 50-year-old, 10 years difference, 10 times 269, 2,691. C is the right answer. Oh boy, here's another one. Okay, so I'm looking at performance or accuracy. So the model gives predictions, correct predictions, 97.7% of the time. No, we never use the multiple R. Prediction should be within 95.4% of actual. No. That On very few occasions will model predictions be off by more than 1,658 from actual. Where did that come from? So I'm looking at performance. So I'm looking at the first box. Standard error is 829. If I double that, I get 1,658. Predictions should, most of the time, are not off by more than 2 standard errors. 2 standard errors in this case is 1,658. Predictions are usually $829 too high. No, they're usually off by, on average, $829. What is R squared? R squared, there's this noise, the scatter, and that how can you explain why is there so much scatter? Well, part of the reason is because of the different ages of the different clients. And actually age accounts for about 95% of the noise that's taking place. So if by using this model, you've reduced the noise by about 95%. That's what R squared is. So, oh, here we go. Another one that's asking this type of thing. The estimates of the coefficients will be correct 95% of the time. No, never. Okay. I'm looking at the coefficients, so I'm going to look at the bottom table, not the top table. The estimate, $269, of the impact of additional year of age is often off by $1.90, but it's rarely off by more than $3.80. So it's often off by 1 standard error, rarely off by more than 2. That's what standard error is. And the standard error of that coefficient is 1.9. So this one says the C is the intercept could be as low as minus 3,559 or as high as 79.53. No, this is the intercept. This is how accurate it is, how far off it is. And D, the model cannot be trusted to give valid predictions. No, it's got a really high R square, suggesting it's a pretty decent model. So I go through these because test 4 covers multiple regression, covers these same issues as in simple linear regression. You just saw simple models there. Multiple regression, it's the same issues, it just with more variables. So we spent 2 weeks going from data understanding and preparation to modeling. And so modeling, we may start off exploring things, but we have a specific objective in mind. There's intent here. We're trying to make predictions, generally with a model. That the regression analysis that we've used is commonly used for value estimation and causal analysis. That's the purpose of why we're doing it. So value estimation is making predictions of a number, like predicting your grade point average based upon what we know about you from high school. Linear regression is a method for estimating a linear function to make a prediction. And we get all kinds of other diagnostic stuff that comes out with that model when we get it. So value estimation is about prediction. Causal analysis is about explanation. And regression we could use for both of those things. But another common prediction thing is classification. So maybe we'd like to not predict your grade point average, but predict whether or not you're going to come back for second year. That's predicting customer churn. That's a very, very common application of classification, trying to find out which customers are going to stay and which ones are going to leave. That we could also do causal analysis on this. Well, like why do they leave? Why would they stay? We're not going to get into those questions now. We're just going to focus on how do we make predictions. So in value estimation, we took a whole bunch of inputs, things we knew about a customer, and used it to predict a number. That was our outcome. In classification, we're going to take a whole bunch of inputs again, but now we're going to predict category. Now, it could be many categories. Maybe I'm trying to predict or guess what the ethnicity is of a customer without them telling me. And so I have different categories I could put them into. But those get really complicated. We're going to focus on the simplest case where it's only a binary variable. So I'm only going to predict, are you male or female? Are you going to buy a product or not buy the product? Are you going to stay or leave? So simple ones, accounting. You're trying to predict whether or not it's a valid or a fraudulent transaction. In giving a loan, we're trying to predict whether or not this is a good customer that's going to pay it back or someone that's going to end up in default. That there's a whole bunch of different things that we do that are categories and just two categories. One of the big challenges we run into with classification is measuring accuracy. That the value estimation, we were estimating a number and that we had a potential for error. I kept going on about standard error. How close is our prediction? But what are large and small errors when you're doing classification? Like you predicted a customer would renew their cell phone contract, they didn't. That's an error. Is it a big one or a small one? We predicted that a transaction was valid, but it actually was fraudulent. We predicted someone would default on the loan and didn't approve the loan, but it turned out, no, this would have been a good customer. We predicted you were going to graduate, but you dropped out. That our predictions are wrong, but they're very different. There wasn't any size to the error. It was either right or it was wrong. When we're looking at classification, this is one where we are looking at what percentage of the time are our predictions correct. So that mistake that many people were doing with R squared and thinking it reflected 95% of the predictions are correct. No, that's not what R squared is. But that would be a good type of measure to use with a classification model. So what percentage of the time did we make correct classification? Or maybe we're just interested in the fraudulent transactions. So what percentage of the fraudulent transactions were identified as fraudulent? That how many did we catch? Or the percentage of valid ones that we identified as being valid? Now, if you make a mistake in making those, those are all nice outcomes, but sometimes you're going to make a mistake. So suppose you rejected a valid transaction, thought it was going to be fraudulent, and it turned out it wasn't. Or you approved a transaction thinking it was valid, and it turned out to be fraudulent. What are the consequences there? They're very different. That in one case, you got a customer upset because their credit card was declined, and they're a good customer. In another case, you approved a transaction, and it was fraudulent. So who's going to cover the cost of that? Probably the bank. It's their mistake. That we're going to get into different types of error rates, and there's a whole bunch of different ones later. Okay. But first we're going to look at some of the models and how they're built. So we have a lot of models that for classification where we start out by estimating a probability, like what's the chance this is fraudulent? And if that probability is sufficiently high, we're going to say, I'm not going to take the risk. I'm going to classify it as fraudulent. But if the risk is very, very small, we'll say, okay, I'll classify it as valid. So I need to estimate a probability, and then I've got to make a decision once I've got that probability. So I'm doing it in two stages. That first stage is estimating a probability, and then the second stage, I apply some type of decision rule. And so we'll have to decide what's the threshold for approving a transaction as being valid or not. That, and you may have different thresholds. If the person is charging, a cup of coffee, it may not be a big deal. But if they were putting the cost of buying a new car on that credit card, um, and it wasn't valid, then yeah, we'd worry about it. Maybe we have different probabilities, different thresholds. So I'm estimating a probability. Probability is a number, not just a 0, 1. It's a whole bunch of different probabilities. So if I'm estimating a number, couldn't I just do, treat it like a value estimation problem? Why not? Couldn't we use regression analysis for classification? It seems to make sense. Well, bit of a problem. Suppose I'm trying to predict at time of hiring whether or not an employee is going to be a good hire or not a good hire. And what I've done is historically, new employees, I've been asked to complete two tests, one on their mathematical skills, more arithmetic than anything, and the other on verbal skills, particularly reading. And so it may well be that in their job, they've got to read manuals on how to use equipment effectively, and to use that equipment, occasionally they'll need to make some, um, set some things, do some mathematical calculations to set the equipment appropriately. So we've got this historical data on it. And let's suppose we went and asked several supervisors to go and pick out of their employees 10 people that they thought were really good employees that they've got and they're proud of. And then pick out 10 employees that they wished we had never hired, that in hindsight, if we were to hire them again, um, we wouldn't. So their rating is a 1, we like them, or a 0, we don't like them. And here we've got their math and verbal scores. So we've got a full data set here. I've just shown you a little bit of it. So I could throw that into my regression model. My rating, I'm trying to predict, and I've got verbal scores, math scores. I just throw it into Excel. It comes out, gives me a formula, this thing here. It's got an R square of 53%. Not great. Standard error of 0.37. Is that big? I don't know. So what's the model telling us? Now, we've had models with binary variables, but they were input variables. What's your gender? Are you a student? That type of thing. This is the outcome. The target is binary. How is that different? Well, let's look some scatter plots. Maybe that'll remind you the difference. Here's a scatter plot of math scores versus rating and verbal scores versus rating. Strange, what's going on? Well, your rating is either a 0 or a 1. I know we're trying to estimate the chance you're a good employee, going to be a good employee, or not be a good employee. Um, so, but the data we've got is not, oh, here's a person that's 70% chance of being good. Here's someone with a 60% chance, and here's someone with a 10% chance. No, we don't get probabilities on each employee. They're either good or they're not good. They're zeros and ones. So I get a very strange scatter diagram. And if I was to put a straight line between their math score and their rating, it looks something like this. And their verbal score, it looks something like that. These are really bizarre looking. Um, so my model is very peculiar in terms of what it produces. But if I just had a threshold and said, I've got 10 good, 10 bad employees. So let's use a threshold. If your probability is bigger than 50%, I'll treat you as being good. And if the probability is less than 50%, I'll treat you as being bad. Well, this is what we get. So here are all the bad employees. And the predicted ratings, they aren't 0, 1. They're a whole bunch of different numbers. And that 8 out of the 10 are below 0.5. 2 of them are just a bit above. So 8 out of 10 bad ones, it predicted correctly. And the other 2 that it was wrong on, it was pretty close. We almost rejected them. For the good employees, 8 out of 10, it guessed correctly. 2 of them, no, it made a mistake. Um, but overall, it's right 80% of the time. It's better than flipping a coin. If I'm just flipping a coin, I'd only be right half the time. So this is actually a pretty good model. The probabilities are sort of garbage, though, that probabilities should range from 0 up to 1. 0 means it can't happen. 1 means it's guaranteed it must happen. And you've got to be on that continuum. You can't get a negative probability. And you can't get a probability that's bigger than 1. And if you'll notice here, I've got a probability that's bigger than 1 over here and a couple that are negative over here. These are really crazy numbers. And it's because I'm using a straight line. It, it, you know, these scatter plots, you would see they come down to negative values if you have a very low math score. And it will give you really high values, bigger than 1 if you had a really high math score. So I shouldn't be using a straight line. So what should I use? Maybe a curve. So instead of putting a straight line through these two clusters of points, suppose I keep it fairly flat, bad, 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 bad. And then as I get to these ones where I'm not sure, your math score is around 350, 380, say. You could be bad, could be good, not sure. So I don't know where. Flip a coin here, maybe. And then if your math score is really high, you tend to all be good. So maybe I could fit this sort of S-shaped curve through there. And that's actually what we're going to end up doing. But where does it come from? It's called a logistic model, Logistica, or IC. Sort of has to do with logs indirectly. So where does it come from? And I'm not going to get into the fancy math because this is really ugly math. But we have two problems. First off, our outcome is binary, 0 and 1. That's problematic. And a straight line can give probability estimates that go below 0 and can go greater than 1. Okay? So if I'm sort of stuck in the 0-1 range, are there ways of adjusting that? Well, you could transform the probabilities into odds. What I mean by odds, if you're familiar with betting, like on sport events, horse racing, for example, or football for that matter, then you might hear of you're betting between two teams, A and B. If 2/3 of the people think team A is going to win and 1/3 think B is going to win, we say the odds are 2-1. There's two people favoring team A for every one person favoring team B. It's just sort of the ratio of, or the how much is bet on one team versus bet on the other team. And so it's expressed as 2-1. That if you had fraudulent transactions happen maybe 10% of the time, okay? 1 in 10. So 90% of the time it's good. We think of the odds ratio as being 1-9. There's one fraudulent one for every 9 good ones. Mathematically, it's if P was your probability, you could rewrite the odds as being P over 1 minus P. And this is interesting because it now takes the numbers 0-1, the probabilities, and makes them 0 up to infinity. So at that top end, now I can go as high as I like. Okay, I don't have to stop at 1. But one of the problems for this, though, is the probabilities are ranging from 0-1. So I got 50%. At the 50% mark, you've got half below, half above. But with odds, a 50-50 ratio is 1. Okay? So all those numbers between 0 and 0.5 are being squished into the range 0-1 now. And all of the probabilities that are from 0.5 up to 1 get spread out over a huge range. So that's not quite fair. So what do we do? It's sort of like having a very, very skewed data set with a lot of it bunched at the bottom and then a very long right tail. Well, economists in particular, they encounter these highly skewed distributions all the time, and they try to make them symmetrical by taking logarithms. Logarithms has a strange effect of taking small numbers, that numbers less than 1, between 0 and 1, and making them negative and spread out from minus infinity up to 0. And then it takes those numbers above 1 and it pulls that tail back in. So numbers could still keep going up really big, but it pulls them back somewhat. So if you take the logarithm of the odds, you'll get more like a bell-shaped curve, and it's nicer numbers to work with. Okay, well, if you then transform it back, if you fit a model to the log of the odds to make it back to a probability, you have to use this ugly looking formula. So it's a lot of work, and we aren't going to get into it. But it is sort of neat as to way of doing these things. And if I used it on this data set, you'll find the probability estimates go from 0 up to a high of 1. But actually, the decisions aren't very good at all with this data set. With this logistic model, my performance is actually worse than my really stupid straight line model. So what's going on here? Well, maybe it's just that data set. Let me show you a different data set. That, remember, we looked at predicting credit card balances and noticed that students and non-students were very different. Could we use credit card balance, rating, income, and work the other way and try to predict whether or not the person holding the card was a student? Well, you could. So I could fit a linear model saying student 0 or 1 is an intercept. I've got the income variable, the rating variable, the balance variable, and noise. It's got an R square around 60%. Not bad. Standard error is kind of big. That is the model really any use? Well, the best way to evaluate that is go and see what's its predictions like. Did it make good classifications? So I just used a simple threshold of 0.5. If the probability was more than 0.5, you're a student. If it's less than 0.5, you're not a student. And on that rule, it turns out that here's what I get out of my predicted probability, and whether or not yes or no. And the probabilities are pretty awful. They ranged all over the place. A lot of them here in the low end of things. But so if the probability is less than 0.5, I'm going to say you're not a student. And if it's more than 0.5, I'm going to say you are a student. Overall, 98.5% of the cases, it predicted correctly. It did a really, really good job. It was great. Um, that so that you know, it may not be giving good probability estimates, but classifications seem to be working quite well. To do the logistic one, I had to use Solver to do this. There's a long process you go through. I'm not going to get into it, but I built a thing in Solver to crank out my model, and it got 99% right. So a little bit better than the other model, and closer to 100%. So it was quite good. What was interesting is the probability estimates. That when you look at the probabilities, you get some of them are like this one, 6E09. So that's like moving the decimal place 9 places to the left. Here, I've got it down here. 0.00000000601. And if you are a student, probability was 0.9968, like almost 1. Really, really good. And if I did a histogram of all the probability estimates, here are all the people that weren't students. And it gave a probability that was very, very close to 0 for them. And here are the students, and it gave probability estimate that was almost equal to 1. And then it struggled with half a dozen that were in between. So logistic gives nice probability estimates, which gives you a little more confidence that the model is making better classification decisions. Okay. So what I got out of all this, well, linear regression can be used to estimate the chance of being in a category. It can be used for classification. I need a decision rule, but I could do it. But logistic regression is much better at probability estimates. It's complicated. It's a lot more computing power needed. Um, we've looked at R squared and standard error. Those things don't belong here. Okay, because they were sort of to do with estimating probabilities. I'm more interested in what the classifications are at the end, and that I can't come out with an R square measured for logistic regression. There's some that have been proposed, but they're not very good, so I wouldn't bother pursuing that. You're looking at how often are you making good classifications. So it's more complicated here in building it. Remember when we built models before, we looked at residuals. We looked at R squared, we looked at standard error. None of these things are meaningful, that we aren't going to be able to use them. We're going to look at performance measures later, okay? And we'll do that in chapter 11. Don't worry about it for now. I should mention before we run away and close it up, a completely different approach that called a discriminant function. And this is, again, a very old technique. It goes back to the beginning of the 20th century, actually. And if you could imagine, and this one I'm looking at the math score, the verbal score. Here where the blue dots are the good employees, the orange triangles are the bad ones. I could almost draw a line here and separate the good guys from the bad guys. And if you're above the threshold, you're good. If you're below, you're bad. So I've got a function here, this line, that discriminates between the good and the bad. We call it a discriminant function. And it doesn't have to be a straight line. It can be curved. It can take on other forms. If you look at the credit card data and look at credit rating, here's credit rating. Here I've put the dots. The blue dots are those that aren't students. The orange dots are the students. Okay? And you'll see that it's almost like, except for a bunch of outliers that I've got here, these were probably those 5 at the end of that exercise that seem to be not conforming with everybody else. But I could put a line here that separates the blues from the oranges. So a discriminant function could be nonlinear. We're not going to get into this. I'm just making you aware. This is another type of approach of just building a fence. And depending on which side of the fence you're on, you're a good guy, you're a bad guy. And we'll make some mistakes in doing so. We're not perfect, but we get most of them right. Okay? And we can get into more complicated things that you can have sets of different rules. We'll actually look at some of this stuff later on in the term. It's sort of like chopping it up in different groups and putting a whole bunch of different fences in place, but we'll leave that to another time. Okay, so this is one of the most common applications in data mining, is classification. And there are actually a large number of very different strategies for doing it. And we've just looked at a couple. The idea of a formula to predict a probability and using linear regression, or this curvy thing, logistic regression, or building a fence and separating them that way. That we're going to look at another one on Wednesday, and then we'll take a break to study probability and come back and show you a couple more methods that you could possibly use. Okay. So let's leave this for today, and it'll be interesting to show you the one that we have next class. It's completely different. It looks at, are you similar? You look like your mother or your father. Okay, that's it, folks. And hopefully I turn this off properly. Whoops, where am I here? There we go. And oops, where's my